The multiverse theory existed long before strange superheroes slung their way through wondrous landscapes on the page and the silver screen. Scientists, authors, researchers, mathematicians, and even some rather insane people have levied their opinions, and we're here to sort out the facts as best we can. Get ready for multiverse madness. What is the multiverse? A multiverse is a hypothetical cluster of multiple universes. Together, these universes contain everything: the entirety of space, time, matter, energy, data, and the physical laws and constants that define them. The various universes within the multiverse are called parallel universes, other universes, alternate universes, or many worlds. Early recorded instances of the idea of unlimited worlds existed in the philosophy of ancient Greek atomism, which suggested that infinite parallel worlds emerged from the clash of atoms. In the 3rd century BCE, the philosopher Chrysippus indicated that the world eternally expired and regenerated, effectively presenting the existence of multiple universes across time. The idea of numerous universes became more defined in the Middle Ages. In Dublin in 1952, Erwin Schrödinger delivered a lecture in which he jokingly cautioned his audience that what he was about to say might seem lunatic. When his equations appeared to describe several different histories, he said that these were not alternatives, but all happened simultaneously. This sort of duality is called superposition. The term was first used in fiction and its contemporary physics context by Michael Moorcock in his 1963 SF Adventures novella, The Sundered Worlds, part of his Eternal Champion series. Multiple universes have been hypothesized in cosmology, physics, astronomy, religion, philosophy, transpersonal psychology, music, and books, particularly in science fiction, comic books, and fantasy. In these contexts, parallel universes are also called alternate universes, quantum universes, interpenetrating dimensions, parallel universes, parallel dimensions, parallel worlds, parallel realities, quantum realities, alternate timelines, alternate dimensions, and dimensional planes. The physics community has discussed the various multiverse theories over time. Famous physicists are split on whether any other universes exist beyond our own. Some physicists declare the multiverse is not a legitimate topic of scientific investigation. Apprehensions have been raised about whether endeavors to exempt the multiverse from experimental validation could deteriorate public confidence in science and eventually damage the study of fundamental physics. Some have claimed that the multiverse is a philosophical concept rather than a scientific hypothesis because it cannot be empirically falsified. The ability to debunk a theory using scientific experiments is a critical standard of the accepted scientific approach. Paul Steinhardt has famously argued that no experimentation can rule out a theory if the theory provides for all possible outcomes. In 2007, Nobel laureate Steven Weinberg indicated that if the multiverse existed, the hope of finding a rational explanation for the precise values of quark masses and other constants of the standard model that we observe in our Big Bang is doomed, for their values would be an accident of the particular part of the multiverse in which we live. Multiverse evidence. Around 2010, scientists such as Stephen M. Feeney studied Wilkinson Microwave Anisotropy Probe, or WMAP for short, data. They claimed to discover evidence indicating that this universe collided with other parallel universes in the distant past. However, a more detailed study of data from the WMAP and the Planck satellite, which has a resolution 3 times higher than WMAP, did not show any statistically substantial evidence of such a bubble universe crash. In addition, there was no proof of any gravitational force of other universes on ours. Multiple opinions. In his 2003 New York Times opinion piece, A Brief History of the Multiverse, author and cosmologist Paul Davies offered an assortment of opinions that multiverse theories are non-scientific. For a start, how is the existence of the other universes to be tested? To be sure, all cosmologists accept that there are some regions of the universe that lie beyond the reach of our telescopes, but somewhere on the slippery slope between that and the idea that there is an infinite number of universes, credibility reaches a limit. As one slips down that slope, more and more must be accepted on faith, and less is open to scientific verification. Extreme multiverse explanations are therefore reminiscent of theological discussions. Indeed, invoking an infinity of unseen universes to explain the unusual features of the one we do see is just as ad hoc as invoking an unseen creator. The multiverse theory may be dressed up in scientific language, but in essence, it requires the same leap of faith. Paul Davies, The New York Times, A Brief History of the Multiverse. George Ellis, writing in August 2011, delivered a criticism of the multiverse and pointed out that it is not a formal scientific theory. He admits that the multiverse is thought to exist far beyond the cosmological horizon. He stressed that it is theorized to be so far away that any proof that will ever be found is unlikely. Ellis also clarified that some theorists do not believe the lack of empirical testability and falsifiability is a significant concern, but he is opposed to that line of thinking. Many physicists who talk about the multiverse, especially advocates of the string landscape, do not care much about parallel universes per se. For them, objections to the multiverse as a concept are unimportant. Their theories live or die based on internal consistency and, one hopes, eventual laboratory testing. Ellis states that scientists have proposed the idea of the multiverse to define the nature of existence. He points out that it eventually leaves those questions unresolved because it is a metaphysical issue that empirical science cannot resolve. He claims that observational testing is at the heart of science and should not be abandoned. As skeptical as I am, I think the contemplation of the multiverse is an excellent opportunity to reflect on the nature of science and on the ultimate nature of existence. Why we are here. In looking at this concept, we need an open mind, though not too open. It is a delicate path to tread. Parallel universes may or may not exist. The case is unproved. We are going to have to live with that uncertainty. Nothing is wrong with scientifically based philosophical speculation, which is what multiverse proposals are, but we should name it for what it is. George Ellis, Does the Multiverse Really Exist? Scientific American. Philosopher Philip Goff contends that the inference of a multiverse to explain the apparent fine-tuning of the universe is an example of inverse Gambler's fallacy. How is the multiverse classified? Max Tegmark and Brian Greene have created classification schemes for the various theoretical types of multiverses and universes that they might contain. Max Tegmark's 4 levels. Cosmologist Max Tegmark has delivered a taxonomy of universes beyond the familiar observable universe. The 4 levels of Tegmark's classification are positioned such that subsequent levels can be comprehended to contain and grow upon previous levels. They are briefly described as the following. Level 1, an extension of our universe. A prediction of cosmic inflation is the existence of an infinite ergodic universe, which, being infinite, must contain Hubble volumes realizing all initial conditions. Accordingly, an infinite universe will include many Hubble volumes, all with the same physical laws and constants. Regarding configurations such as the distribution of matter, almost all will vary from our Hubble volume. However, because there are infinitely many, far beyond the cosmological horizon, there will ultimately be Hubble volumes with matching and even identical configurations. Tegmark estimates that an equal volume to ours should be about 1,010,115 meters away from us. Given infinite space, there would be an endless number of Hubble volumes identical to ours in the universe. This tracks directly from the cosmological principle, wherein it is believed that our Hubble volume is not unique or distinctive. Level 2. Universes with different physical constants. In the eternal inflation hypothesis, a variant of the cosmic inflation theory, the multiverse or space is stretching. It will continue doing so forever, but some parts of space stop stretching and form different bubbles, like gas pockets in a loaf of rising bread. Such bubbles are embryonic level 1 multiverses. Different bubbles may undergo further spontaneous symmetry breaking, which results in various properties, such as multiple physical constants. Level 3. Many worlds interpretation of quantum mechanics. Hugh Everett 3RD's Many Worlds Interpretation, or MWI for short, is one of several mainstream interpretations of quantum mechanics. In short, one part of quantum mechanics is that specific observations cannot be anticipated clearly. Instead, there is a range of possible observations, each with a different possibility. According to the MWI, each potential observation conforms to a separate universe. Suppose a six-sided die is thrown and that the result of the throw corresponds to quantum mechanics observable. All 6 possible ways the dice can fall correspond to 6 different universes. Tedmark contends that a level 3 multiverse does not include more possibilities in the Hubble volume than a level 1 or level 2 multiverse. In effect, all the various worlds created by splits in a level 3 multiverse with the same physical constants can be found in some Hubble volumes in a level 1 multiverse. Tedmark writes, in level 3, they live on another quantum branch in infinite dimensional Hilbert space. Also, all level 2 bubble universes with different physical constants can, in effect, be found as worlds formed by splits at the moment of spontaneous symmetry splitting in a level 3 multiverse. According to Yasunori Nomura, Raphael Bauso, and Leonard Susskind, this is because global spacetime appearing in the eternally growing multiverse is a repetitious concept. This implies that the multiverses of levels 1, 2, and 3 are, in fact, the same thing. This hypothesis is referred to as multiverse or quantum many worlds. Yasunori Nomura says this quantum multiverse is fixed and time is a simple illusion. Level 4. Ultimate ensemble. The ultimate mathematical universe hypothesis is Tedmark's hypothesis, known as the MUH, mathematical universe hypothesis. This level assumes all universes are equally real, which can be described by different mathematical structures. Tedmark's MUH is, our external physical reality is a mathematical structure. The physical universe is not merely described by mathematics, but as mathematics, especially a mathematical structure. Mathematical existence equals physical existence, and all systems that exist mathematically exist physically. Observers, including humans, are self-aware substructures, or SAS for short. In any mathematical system involved enough to have such substructures, they will subjectively perceive themselves as existing in a physically real world. The idea can be deemed a form of Pythagoreanism or Platonism. It suggests the existence of mathematical entities, a form of mathematics that disavows that anything exists except mathematical objects, and a traditional expression of ontic structural realism. Tedmark argues that the hypothesis has no free parameters and is not observationally ruled out. Thus, he claims, it is favored over other theories of everything by Occam's razor. Tedmark also believes in augmenting the MUH with a second assumption, the computable universe hypothesis, or CUH for short, which says that computable processes represent the mathematical structure of our external physical reality. The MUH is connected to Tedmark's categorization of 4 levels of the multiverse. This categorization posits a nested scale of increasing variety, with worlds connected to different initial prerequisites. Level 1, physical constants. Level 2, quantum branches. Level 3, and other equations or mathematical structures. Level 4. However, prominent computer scientist Jürgen Schmidhuber says that the set of mathematical structures is not even well defined. It admits only universe models describable by constructive mathematics, that is, computer programs. Schmidhuber explicitly includes universe representations describable by non-halting programs whose output bits converge after a finite time. However, the intersection time itself may not be predictable by a halting schedule due to the undecidability of the halting problem. He also explicitly examines the more fixed ensemble of fast computable universes. The American theoretical physicist and string theorist Brian Greene discussed 9 types of multiverses. The quilted multiverse operates only in an infinite universe. With endless space, every possible event will happen unlimited times. However, the speed of light stops us from being aware of these other identical areas. Inflationary. The inflationary multiverse comprises various pockets in which inflation fields crumple and form new universes. Brain. The brain multiverse version proposes that our entire universe lives on a membrane or brain which floats in a more elevated dimension or bulk. In this bulk, there are other membranes with their universes. These universes can interact with each other, and when they clash, the violence and energy created are more than enough to give rise to a Big Bang. The brains drift near each other in bulk, and every few trillion years, drawn by gravity or some other force we do not understand, crash and slam into each other. This repeated contact gives rise to multiple or cyclic Big Bangs. This individual theory falls under the string hypothesis umbrella as it needs extra spatial dimensions. Cyclic. The cyclic multiverse has multiple brains that have crashed, causing Big Bangs. The universes reflect and pass through time until they are pulled back together and again hit, eliminating the old contents and forming them anew. Landscape. The landscape multiverse depends on string theory's Calabi-Yau spaces. Quantum fluctuations drop the shapes to a lower energy level, forming a pocket with a set of laws different from that of the surrounding area. Quantum. The quantum multiverse forms a new universe when a diversion in events happens, as in the many worlds understanding of quantum mechanics. Holographic. The holographic multiverse is derived from the idea that the surface area of a space can encode the contents of the area's volume. Simulated. The simulated multiverse exists on complicated computer systems that simulate whole universes. Ultimate. The ultimate multiverse includes every mathematically possible universe under different laws of physics. There is a series of infinite, self-sustaining cycles in several theories, for example, an eternity of Big Bangs, Big Crunches, and Big Freezes. String theory and its higher dimensional extension, M theory, have envisaged a multiverse of a somewhat different kind. These theories require the presence of 10 or 11 spacetime dimensions, respectively. The extra 6 or 7 dimensions may either be compactified on a microscopic scale, or our universe may be localized on a dynamical 3 plus 1-dimensional object, a D3 brain. This opens up the possibility that other brains could support other universes. Black hole cosmology. Before we dive into black hole cosmology, let's look at what a black hole is. A black hole is an area of spacetime that exhibits gravitational acceleration so powerful that nothing, no electromagnetic radiation such as light or particles, can escape from it. The theory of general relativity estimates that an adequately compact mass can change spacetime to form a black hole. The edge of the area from which there is no possible escape is called the event horizon. Though the event horizon significantly affects the circumstances and fate of an object that crosses it, no regionally discernible features appear to be seen. A black hole will act as an intense black body because it reflects no light in many ways. Furthermore, quantum field theory in curved spacetime predicts that event horizons emit Hawking radiation. This radiation has the same spectrum as a black body of a temperature contrary proportional to its mass. This temperature comes on the order of billionths of a Kelvin for black holes of stellar mass, which makes it impossible to observe. When were they first studied? Objects with gravitational fields too strong for light to escape were first contemplated by philosophers Pierre-Simon Laplace and John Michell in the 18th century. The first modern solution of general relativity, which would go on to characterize a black hole, was found by physicist and astronomer Karl Schwarzschild in 1916. Even though its interpretation as a region of space from which nothing can escape was first published by a professor of physics David Finkelstein in 1958. Black holes were long thought to be a mathematical curiosity. During the 60s, theoretical work showed black holes were a generic prediction of general relativity. The discovery of neutron stars by astrophysicist Jocelyn Bell Burnell in 1967 sparked interest in the gravitational collapse of compact objects as a possible astrophysical reality. Black holes of stellar mass are known to form when very massive stars collapse at the end of their life cycle. After a black hole has taken shape, it can continue to grow by absorbing mass from whatever is around it. The absorption of other stars that merge with other black holes may even form a supermassive black hole home to millions of solar masses. It's often believed that supermassive black holes exist in the centers of most galaxies. How are black holes found? The existence of a black hole can be deduced through its interaction with electromagnetic radiation, such as visible light and other types of matter. Matter which falls onto a black hole can form an external accretion disk that becomes heated by friction. That's how some of the brightest objects in the universe are created. If other stars are orbiting a black hole, their orbits can be used to figure out a black hole's location and mass. Observations like these can be used to prohibit possible alternatives like neutron stars. Astronomers have used these means to identify many stellar black hole candidates within binary systems and establish that the radio source, Sagittarius A, is at the core of the Milky Way galaxy. It is therein you'll find a supermassive black hole of about 4.3 million solar masses. That's huge. On February 11, 2016, the Laser Interferometer Gravitational Wave Observatory, or LIGO collaboration, announced the initial direct findings of gravitational waves. These waves also represent the first witnessing of a black hole merger. As of December of 2018, 11 gravitational wave events were observed that originated from 10 merging black holes, along with one binary neutron star merger. Then on April 10, 2019, the first ever direct image of a black hole and its vicinity was captured and subsequently published. The idea of a body so vast that not even light could escape was once suggested by astronomical pioneer and English clergyman John Michell in a letter he published in November of 1784. Michell's simple calculations showed that such a body might even have the same density as the Sun. He concluded that such a body would take shape when a star's diameter outgrows the Sun's by a factor of 500 and the surface escape velocity surpasses the speed of light. Michell was correct when he noted that such supermassive but non-radiating bodies might be detected by their gravitational effects on nearby visible bodies. Scientists were initially excited by the proposal that massive yet invisible stars may be hiding in plain sight, but that enthusiasm waned when light's wave-like nature became apparent during the early 19th century. If light were a wave instead of a corpuscle, it isn't clear what influence gravity would have on escaping light waves. In this day and age, relativity theorists discredit Michell's idea that a light ray shooting directly from the surface of a supermassive star could be slowed down by the star's gravity, thereby stopping and free-falling back onto the star's surface. What did the genius Einstein have to say about black holes? In 1915, the great Albert Einstein created his theory of general relativity, having earlier proven that gravity influences light's motion. A few months later, German physicist and astronomer Karl Schwarzschild found a solution to Einstein's field equations, which described the gravitational field of a spherical mass and a point mass. Several months after, Schwarzschild, along with a student of Dutch physicist Hendrik Lorentz named Johannes Drost, independently found the same solution for the point mass, which led to them writing extensively about its properties. Their conclusion exhibited some strange behavior at what is now referred to as the Schwarzschild radius, where it became singular. This means that some of the terms in the Einstein equations had become infinite. The essence of this plane was not quite grasped at the time. Then in the year 1924, astronomer and physicist Arthur Eddington proved that the singularity disappeared after a change of coordinates. Still, it took until 1933 for mathematician and astronomer Georges Lemaître to realize that this meant that the singularity at the Schwarzschild radius was a non-physical coordinate singularity. Physicist and astronomer Arthur Eddington did, however, speak about the possibility of a star with mass compressed to the Schwarzschild radius in a 1926 book, noting that Einstein's theory allows us to rule out overly large densities for visible stars like Betelgeuse, because a star of 250 million kilometer radius could not possibly have so high a density as the Sun. Firstly, the force of gravitation would be so incredible that light wouldn't be able to escape from it. The rays would fall back to the star like a stone would if dropped to the Earth. Secondly, the red shift of the spectral lines would be so massive that the spectrum would shift out of existence. Thirdly, the mass would produce so much curvature of the spacetime metric that space would envelop the star, leaving us outside. In 1931, American astrophysicist Subramanian Chandrasekhar concluded that using special relativity, a non-rotating body of electron-degenerate matter above a certain limiting mass would have no stable solutions. Many of his peers, such as Eddington and Soviet physicist Lev Landau, opposed his findings. Eddington and Landau maintained that some yet unknown mechanism would prohibit the collapse. The pair was partially true. A white dwarf that was slightly more massive than the Chandrasekhar limit would indeed collapse into a neutron star, which was itself stable. But in 1939, theoretical physicist Robert Oppenheimer, alongside others, predicted that neutron stars above another limit would collapse even more for the reasons given by Chandrasekhar. Oppenheimer concluded that no law of physics was likely to intervene and prohibit at least some stars from collapsing to black holes. Oppenheimer and his fellow authors said that the singularity at the boundary of the Schwarzschild radius would show that this was the boundary of a bubble where time stopped. This remains a valid point of view for many outside observers, but not for infalling observers. This property showed that the collapsed stars were called frozen stars, as an outside observer would only see the surface of the star that had been frozen in time at the moment when its collapse would take it to the Schwarzschild radius. In 1958, Professor of Physics David Finkelstein identified the Schwarzschild surface as an event horizon. He called it a perfect unidirectional membrane. Causal influences can cross it in only one direction. This didn't strictly contradict Oppenheimer's results, but instead it extended them to include the point of view of infalling observers. Finkelstein's answer extended the Schwarzschild solution for the future of observers falling into a black hole. American mathematician Martin Kruskal had already discovered a complete extension and was urged to publish his findings. Why don't we know a lot about black holes? Because a black hole has only a few internal parameters, most of the information about the matter that went into forming the black hole is lost. Regardless of the type of matter that goes into a black hole, only information concerning the total mass, charge, and angular momentum is conserved. As long as black holes were thought to persist forever, this information loss is not that problematic. According to the holographic principle, the information can exist inside the black hole, which is inaccessible from the outside but is represented on the event horizon. However, black holes slowly evaporate by emitting Hawking radiation. This radiation does not appear to carry any additional information about the matter that formed the black hole, meaning that this information seems to be gone forever. Whether information is truly lost in black holes, the black hole information paradox has divided the theoretical physics community. In quantum mechanics, loss of information corresponds to the violation of vital property called unitarity, which has to do with the conservation of probability. It has been argued that loss of unitarity would also imply a violation of energy conservation. Over recent years, evidence has been building that information and unitarity are preserved in a full quantum gravitational treatment of the problem. According to quantum field theory in curved spacetime, a single emission of Hawking radiation involves two mutually entangled particles. The outgoing particle escapes and is emitted as a quantum of Hawking radiation. The black hole swallows the infalling particle. Assume a black hole formed a finite time in the past and will fully evaporate away in some finite time in the future. Then it will only emit a limited amount of information encoded within its Hawking radiation. Assume that more than half of the information had already been emitted at the time. According to widely accepted research by physicists like Don Page and Leonard Susskind, an outgoing particle emitted at time must be entangled with all the Hawking radiation the black hole has previously emitted. This creates a paradox. A principle called monogamy of entanglement requires that, like any quantum system, the outgoing particle cannot be fully entangled with two independent systems at the same time. Yet here, the outgoing particle appears to be entangled with both the infalling particle and, independently, with past Hawking radiation. To resolve the paradox, physicists may eventually be forced to give up one of three time-tested theories: Einstein's equivalence principle, unitarity, or existing quantum field theory. One possible solution, which violates the equivalence principle, is that a firewall destroys incoming particles at the event horizon. A 2016 analysis of LIGO data shows tentative signs of echoes caused by a fuzzy event horizon. Such echoes may be possible in firewall or fuzzball theories, but should not occur in classical general relativity. Over the next 2 years, additional LIGO data should establish whether the echoes were just random noise or whether they are instead evidence of a violation of classical general relativity. Black hole cosmology is a cosmological model. The observable universe is the interior of a black hole existing as one of the possibly many universes inside a larger universe. This includes the theory of white holes on the opposite side of spacetime. The concept of other universes has been proposed to explain how our universe appears to be fine-tuned for conscious life as we experience it. If there were a large, possibly infinite, number of universes, each with perhaps different physical laws or different fundamental physical constants, then some of these universes, even if very few, would have the combination of statutes and basic parameters that are suitable for the development of matter, astronomical structures, elemental diversity, stars, and planets that can exist long enough for life to emerge and evolve. The weak anthropic principle could then be applied to conclude that we as conscious beings would only exist in one of those few universes that happen to be finely tuned, permitting the existence of life with developed consciousness. Thus, while the probability might be tiny that any particular universe would have the requisite conditions for life as we understand life, those conditions do not require intelligent design to explain the conditions in the universe that promote our existence in it. An early form of this reasoning is evident in Arthur Schopenhauer's 1844 work Von der Nichtigkeit und dem Leiden des Lebens, where he argues that our world must be the worst of all possible worlds because if it were significantly worse in any respect, it could not continue to exist. This brings us to Occam's razor theory. Occam's razor. Occam's razor, also known as the principle of parsimony or the law of parsimony, is the problem-solving regulation that entities should not be multiplied beyond necessity. It is generally comprehended that with contending theories or reasons, the more straightforward one, for example, a standard with fewer parameters, is desired. Although he never used these words, the idea is often attributed to English Franciscan Friar William of Ockham, an academic philosopher and theologian. This philosophical razor advocates that when presented with competing hypotheses about the same prediction, one should choose the solution with the fewest assumptions. This is not conveyed to be a way of choosing between theories that make various predictions. Likewise, in science, Occam's razor is employed as an abductive heuristic in creating theoretical models instead of as a rigorous arbiter between candidate standards. In the scientific method, Occam's razor is not deemed an irrefutable principle of logic or a scientific derivative. The preference for simplicity in the scientific method is established on the falsifiability criterion. There may be an enormous, perhaps even unbelievable, number of potential and more complicated alternatives for each acknowledged explanation of a phenomenon. Since failing reasons can always be burdened with ad hoc hypotheses to prevent them from falsifying, simpler theories are preferable to more involved ones because they tend to be more testable. Supporters and critics disagree about how to apply Occam's razor. Critics contend that proposing an almost infinite number of unobservable universes to define our universe is contrary to Occam's razor. However, advocates say that the suggested multiverse is more straightforward than a single idiosyncratic universe of Kolmogorov complexity. For example, Tegmark argues, an entire ensemble is often much simpler than one of its members. This principle can be stated more formally using the notion of algorithmic information content. The algorithmic information content in a number is, roughly speaking, the length of the shortest computer program that will produce that number as output. For example, consider the set of all integers. Which is simpler, the whole set or just one number? Naively, you might think that a single number is simpler, but the entire set can be generated by quite a trivial computer program, whereas a single number can be hugely long. Therefore, the whole set is actually simpler. Similarly, the higher-level multiverses are simpler. Going from our universe to the level 1 multiverse eliminates the need to specify initial conditions. Upgrading to level 2 eliminates the need to specify physical constants. And the level 4 multiverse eliminates the need to specify anything at all. A common feature of all 4 multiverse levels is that the simplest and arguably most elegant theory involves parallel universes by default. To deny the existence of those universes, one needs to complicate the theory by adding experimentally unsupported processes and ad hoc postulates, finite space, wave function collapse, and ontological asymmetry. Our judgment, therefore, comes down to which we find more wasteful and inelegant, many worlds or many words. Perhaps we will gradually get used to the weird ways of our cosmos and find its strangeness to be part of its charm. At the end of the day, the subject of a possible multiverse is one so complex yet completely endearing that it will be argued over and theorized for the duration of humankind. Will we ever get our answers? Are we plugged into some form of a matrix? Maybe we're riding waves emitted from a black hole. Who knows? Our fascination will remain ongoing,